This is also inside. If you think that there is surface outside like this, okay, suppose you have a big circle and the integration over here, okay, then the pressure at infinity is 0 and velocity at infinity is 0. That is far field condition. Okay? Okay? So, you can regard this as an interior or exterior, depending on the surface you are considering. The important point is the surface or the R, internal space, I mean, the volume enclosed by the surface has to be source free. Has to be source free. In other words, this field has to be satisfied with homogeneous wave equation. Okay? Then you might ask, what if there is a source over here? Then you just integrate those, including the source. Then velocity over here and the velocity over here, then I integrate along this surface, cancel out. Okay? Pressure over here and pressure over here is cancel out. And cancel out again. So what you do is you just surround all the sources and use this Kirchhoff-Helmholtz integral equation. Okay? And some text use minus 1 over 4 pi over here. But doesn't matter if we can include that factor in Green's function. Right? It doesn't really matter. But physically, this Kirchhoff-Helmholtz integral equation says us the way to predict the sound field at any point R due to vibrating surface or pressure source, whatever, any kind. So as a conclusion, we do know how to get the pressure at any point due to the sources. Right? But I ask you, why then we study the special case breathing sphere and trembling sphere? Why? Why? Dong-Su, why? We absolutely know the way to predict the sound at any point if we know how the obstacle or how the object we are considering is vibrating. Huh? Why we study the breathing sphere and the trembling sphere? First reason is this is theoretically correct, but does not provide any physical, tangible feeling. Right? So let us start with the simplest case to figure out what's really happening in radiation field. So first we studied the breathing sphere, and then we had a question. Actually, I had a question, not you. What if we have the sphere is oscillating in this direction? Okay? Okay? And then what I am going to expand is, what if I have a wall and then I have a piston that is oscillating with the u0 exponential j omega t, and say this has a radius of a, like a small piston with the radius a is oscillating with the magnitude of u0. Okay, and we want to see the radiation field due to this, and the trembling sphere with radius a, and the breathing sphere radius a. And we want to compare that to figure out, to understand the radiation phenomena. Okay? Seju? Okay? Okay. We are attempting to understand the radiation characteristics or radiation wave field generated by general vibrating structure like this, or like this, or like this. Okay? We do know how to predict the sound radiated by this vibrating sphere. Can be done by using Kirchhoff-Helmholtz integral equation. I measure the velocity over the surface and integrate using that integral formula, and I invite some Green's function that satisfies the inhomogeneous wave equation. Okay? That equation really assures us to get a solution or wave generated by this vibrating surface. Okay? But that is too general. Therefore, we start with the simplest case. So one is a breathing sphere, and the other one is a trembling sphere, and the other one next we will study is the baffled piston. This is a baffle, and this is piston. How does it radiate? Okay? Seju, you got it? Okay? What about you? You? Okay? It's very hot, right? Is it? You want to sleep, huh? Okay? Everybody happy over there? Okay? So it's very simple. The strategy is very simple, but the details is not simple. Okay? Details, we have to derive it. Get it? Oh, one student is missing. Right? Okay. So, let's see how the wave is generated by this trembling sphere. Its solution of this trembling sphere would be look like this. And then you might ask him, why? How did you get solution? Yeah. How did you get that solution?